Hi, welcome back to my channel. Well, in this video we'll try to learn what are the basic concepts which are involved in execution of factorial experiments, especially when we are interested to study their individual as their combined effect. So let us proceed. Factorial experiments. When two or more number of factors are investigated simultaneously in a single experiment, such type of experiments are known as factorial experiments. Now the important thing here is equal precision. That means whenever we are interested to study the effect of various factors which might involve equal or unequal number of levels, so whenever we are interested to study their effects simultaneously in same experiment, and that too with equal precision, such type of experiments are known as factorial experiments. Now there are two important terminologies involved. One is factor and another one is level of factor. What is factor? A factor refers to a set of related treatments. For example, we may apply different doses of nitrogen to a crop. Hence, nitrogen, irrespective of doses, is a factor. Now, what are the levels of a factor? Different states or components making up a factor are known as levels of that factor. For example, different doses of nitrogen. Now, why factorials are important and why we go for factorial experiments? We have to conduct an experiment to study the performance of a new crop or tree species in an area where it has never been grown before. A sample of pertinent questions that arise for planning such experiments are: what should be the best crop variety? When should the crop be planted, or we can say the date of sowing? Should it be sown directly or transplanted? If sown directly, what would be the seed rate? If transplanted, what would be the age of seedlings? Should the seedlings be drilled or broadcast? Must we use fertilizer? If yes, how much of the major elements are needed? Have we to add minor elements, or do we have to add the minor elements? Is irrigation necessary? What should be the plant to plant and line to line spacing? So a lot of questions arises whenever we are interested to study the performance of a new crop or a variety or a tree species in a given area where it has never been grown. So that is why these factorials are important in a way that this problem may be investigated by varying a single factor at a time using the conventional single factor experiments or complete block designs like completely randomized design, which is also known as zero-way elimination of heterogeneity, RCBD, one-way elimination of heterogeneity, or whenever we are interested to evaluate large number of treatments like in complete block designs or many other complete block designs. For example, an experiment may be conducted with varieties of the crop as treatment to pick up the best variety. Using the best variety, another experiment may be conducted to obtain the date of sowing. Then using the best variety and the optimum date of sowing, another experiment may be conducted to find the optimum level of several other factors like nutrient application, irrigation, and so on, one at a time. The soundness of this approach rests on the assumption that the response to different varieties is independent of the amount of other factors being given. That is, the factors act independent of each other, or these factors act independently to each other. But then this is a big assumption, and such situations are very rare. To make the exposition simple, let us take an example of an experiment involving two factors. One is irrigation and another one is different doses of nitrogen or nitrogen fertilizer. Consider the results of a trial designed to measure the effects of nitrogen with two levels and irrigation again with two levels, both alone and in combination when applied to the rice crop variety or rice crop. The yield of rice crop in quintals per hectare is given below. So we have two irrigations, one at 5 centimeter and another one at 10 centimeter, and the another factor, that is nitrogen, one is at 0 kg per hectare and another one is 60 kg per hectare, and we have different responses here. 10 kgs with first level of irrigation when no nitrogen was given, and this is the first level of irrigation when 60 kg of nitrogen was. So the yield here is 10 quintals per hectare, 30 quintals per hectare, 20 quintals per hectare and 40 quintals per hectare. And if we will take the average of this, that is 20, and here it is 20, and here it is 10, and it is here it is 10. So the effect of nitrogen at first level of irrigation is 30 minus 10. We can say 30 minus 10 is 20, that is 20 quintals per hectare. Or we can say the differences in the responses, of a factor for a fixed level of another factor is known as the simple effect of that factor. So the simple effect of nitrogen at first level of irrigation is 20, and the simple effect of nitrogen at second level of irrigation is this 40 minus 20, that is 20 quintals per hectare. Now in case of irrigation, the effect of irrigation at first level of nitrogen is 20 minus 10, that is 20 minus 10, that is 10, and the effect of irrigation at the second level of nitrogen is 40 minus 30, that is 40 minus 30, which is equal to 10. Now here you can see the simple effects for this one and this one is same, and same is the case for the another factor. So as the effect of nitrogen is same at the levels of the irrigation, or we can say as the effect of irrigation is same at all the levels of nitrogen, hence there is no interaction between nitrogen and irrigation. So we can say the factors are said to interact if the effect of one factor changes as the level of other factor changes also. Take the example here. This is the same example, but the difference here is the simple effect for this and this is different, and so is the case for the another two. Here we can say as the effect of nitrogen is not same at all the levels of the irrigation, hence there is an interaction between the factor A and factor B, which is nitrogen and irrigation. And you can see here it is 20, it is 30, it is 20, it is 20, it is same here but it is different here. Same is the case with this, it is same here but it is different here. So when the factors are said to interact, there means that the effect of one factor changes as the level of the other factors changes. So there are three different types of effects which are involved in assessing this kind of situation, that is simple effect, main effect and interaction effect. Simple effect of a factor is the difference between its responses for a fixed level of other factors, and main effect is simply it is the average of the simple effect, and interaction is defined as the dependence of factor in their responses, or it is measured as the mean of the differences between the simple effect. Now this was the simple effect, or simple effect is simply the differences in the responses for a fixed level of another factor. The fixed level here is nitrogen, this irrigation at first level. So the differences in these two, N1 and N0, it is 20. Now if we take the average of these two, that is the main effect of this nitrogen, and if we seek the mean of the differences between these simple effects, we use to get this interaction effect. If it is equal to 0, that means there is no interaction or there is no dependence, or we can say the factors are not in a position to interact. That means the effect of one factor does not change as the levels of the other factor change, but if it changes, then there is an existence of interaction. So these three effects are very important, and they are involved in assessing this, we can say these factorial experiments. Now there are different types of factorial experiment. One is symmetrical and another one is asymmetrical. Symmetrical means when the levels of the factors which are involved in an experiment, factorial experiment, are same. For example, we have two factors, one has got two levels and another one has got two levels, or we can say the same levels, they are known symmetrical. And when we are when in an experiment there are different or several factors they are involved, or they are having different levels, they are not having same levels in them, then they are known as asymmetrical. The simplest of the symmetrical factorial experiments are the experiments with each of the factors at two levels. If there are n factors each at two levels, it is called 2 raised power n, where power stands for the number of factors. For example, if there is 2 raised power 2, that means two factors which involves two levels. So the power stands for the number of factors, and the base is nothing, it is the level of each factor. So if there are n factors each at 3 levels, it is called as 3 raised power n. Now the simplest of the symmetrical factorial experiments, when I say symmetrical, that means the levels are same. Symmetrical factorial experiment is 2 raised power 2. This is the simplest one. That means there are two factors with two levels. Two factors, say a and b, each at two levels. Say one is at low level, which is denoted by this 0, and another one is at high level. That means this is the first level, this is the second level. So there will be 4 treatment combinations which can be written in this form, 0 0, or we simply can write a0, b0, or 1. That means a and b both are at first or low level. If we write 1 0 or a1 b0 here, or we can simply write a. So these are the 3 different ways how we can write the codes, or we can say to represent a simple 2 raised power 2 factorial, either by this and this and this. They represent both a and b are at first level. If it is 1 0, that means a is at high level, b is at its first level. That means we can simply write a1 or b0, or we can simply write this small a. That means a is at the high level or second level, and b is at the first level. Here a is at the first level or low level, b is at the second level or high level. We can simply write a0 b1, or simply we can write b. That means level a at first level or low, and b at the second level. And if we will write 1 1, we can simply write a1 b1, or simply write ab. This means both are at high level or at their highest level. A and b are at the second level or high level. So we can simply calculate their main and interaction effect by means of this algebraic procedure, which is very simple. So AB, it is simply both these factors are at second level. This is A is at second level, B is at second level, and similar is the case with this. And here that means both these factors are at their initial levels or at low levels. So this is the way how we can get the interaction effects of these factors. So the 3 things are very important in assessing the factorial experiment. One is simple effect, which is nothing, which is the differences between the responses. The second effect is the main effect, is average of the simple effect, and the third one is interaction, which gives an idea whether the two factors are moving in the same direction, or whether there is an existence of association, whether there is a non-existence of association, or we can say whether there is a dependence or independence between the factors, whether they are interacting with each other, or we can say if there is a change in the level of one factor, does it involve in any kind of change in another factor. Now, as far as the traditional analysis of variance which are involved in a conventional RCBD with two factors has a structure like this. So if we have two factors, factor A and B, where small letters represent the levels of the factors, and this is the way how we can get the interaction degrees of freedom, error degrees of freedom, and we can get these sum of squares by those conventional algebraic procedures, and simply divide these sum of squares with their respective degrees of freedom so that we can get the mean square. And we will divide every mean square with its mean square due to error so that we can get f, where we will have a evidence of whether we are going to proceed with this particular hypothesis which has been proposed or not. Now let us take a numerical illustration. For example, the yields of wheat variety C591 in pounds per plot under different treatment combinations carried out in an RCBD design at a research station are given below. It involves two factors. It has got 3 date of sowing, that is S1, S2 and S3, and 4 levels of ammonium sulfate or nitrogen, that is N0, N1, N2 and N3, and it involves 6 replications, 1, 2, 3, 4, 5 and 6 rather than 6 blocks. And the first important thing is to get the basic arithmetic, to get the column totals and row totals, so that we can get the totals for these 12 treatment combination, because 3 multiplied by 4 is 12, and we can get the block totals or replication totals also. So how we are going to proceed or calculate the sum of squares? For that we need to get a two-way total table of these totals of these 12 treatment combinations in a two-way form, which depends upon the number of levels which are involved in both the factors. Say for example, we have 3 different date of sowings and we have 4 different doses of nitrogen. So we'll adjust these totals in this way and get the column totals as well as the row totals, and finally we'll get the grand total here. Now the first thing is to get the correction factors or corrected sum of squares. That is the square of this grand total divided by the number of these observations, because it involves 12 treatment combinations, which is a multiple of both the levels of these factors, and that is 12 multiplied by 6 is 72. Now the total sum of square is very simple to calculate, squaring each and every observation and deducting it with the correction factor. Replication sum of square is very simple to get the replication totals, like this one, this square plus this up to the last replication, then divide it by the number of the treatments which are involved, or not treatments in this case, treatment combination, that is 12. Now the treatment is very simple to get the treatment totals. Here this square up to the last one, whole divided by the number of replications which are involved. Then the sum of square due to date of sowing, that means this square plus this plus this. Now whole divided by the number of replicates and multiple by the number of levels of the opposite factor. That means it has got 4 levels. And in this case, doses due to the nitrogen, or sum of square due to nitrogen doses is this plus, or we can say this square plus this square plus this square plus this square divided by the number of replications and the levels in the opposite factor, that has got 3 levels. So this is the rule which we have to always proceed while calculating manually the sum of squares of a particular factor. Now the interaction of square is very simple. To direct treatment sum of square with the sum of squares of one factor and the sum of square with another factor, so that is 49. So we have got the sum of squares, and we will put all these sum of squares in these respective column of sum of square. And error is very simple to get. To detect this total sum of square with this interaction sum of square due to nitrogen, sum of square due to this date of sowing, and sum of square due to replication, we can get this 182.30. This is very simple to calculate. So once we have got the sum of square, we'll put them in this column, then divide each and every sum of square with its respective degrees of freedom. Now this is very important. It involves 6 replication, that is 6 minus 1 is 5. It has got 3 levels of doses of nitrogen, that is 3 minus 1 is 2, and the doses or the levels for this nitrogen or ammonium sulfate is 4. 4 minus 1 is this, and by means of this we can get the interaction, that is 2 multiplied by 3 is 6, and R minus 1 is 5, and A into B is 3, 4 into 12, 12 minus 1 is 11, 11 multiplied by 5 is 55, and total number of observations 72, 72 minus 1 is 71. So we will divide each and every mean square due to replication with its mean square due to error, mean square due to the doses of or date of sowing with this doses mean square due to nitrogen with mean square due to error, and mean square due to interaction with mean square, so that we can get F. So the tabulated values are already given here, and how these are calculated. These are calculated at 2 degrees of freedom, one due to numerator and another one due to denominator. That means at 55 and 5 and 55 degrees of freedom. Here with 2 with 55, 3 with 55, 6 and 55. So in this case, except replication, all these source of variations are significantly different with respect to a particular level. If we take the example of different doses date of sowing, they are significantly different because the calculated value of F here is greater than its tabulated value. So we can interpret accordingly the other sources of variations also, because the thumb rule is whenever the calculated value of a particular test of significance is greater than its calculated critical value, then we have to reject a particular hypothesis. Say for example, the hypothesis involved that there are no significant difference between the different doses of nitrogen or different date of sowing, or we can say there is no interaction present, there is no dependence between these two factors. But in all these three cases except the replications, the things or the results are significantly different. Now once we have got this up, we need to perform the post-hoc analysis. For post-hoc analysis, we need to get the treatment individual means as well as their interaction means. So we have a two-way table. This is the final table which we have to make. These are all averages. So here we can see if we want to get the critical difference for date of sowing, which involves 3 levels. Since here in denominator this mean square error is 3.31 multiplied by 2, since it is under root twice mean square divided by the number of replicates. But here we have got two factors. In case of date of sowing, here it is 6 multiplied by 4, that is 24, and in case of doses of nitrogen it is 6 multiplied by 3, that is 18. So in denominator the replications must be multiplied by the levels of the opposite factor. So both these critical difference or least significant difference can be calculated accordingly, because all these calculations have been discussed in the previous videos involving analysis of variance CRD, RCBD and LSD. So multiply by the T alpha at error degrees of freedom at 5% level of significance. The error degrees of freedom is fixed here 55, it is 2.004. Then when we multiply it, the critical difference for doses different date of sowing is 1.05, and in this case is 1.2, and in case of interaction. So simply we can say the highest yield was observed in case of first date of sowing. We can interpret like this: the highest average yield 10.85 pounds is obtained with sowing date S1. The average yield significantly decreases as the sowing date increases, you can see. Or here the highest was observed in case of N2 dose, and which is at par with 7 point this with N3, we can say. And the highest interaction was found in case of S1 and N2 followed by S1 and N3. So this was significantly different from few of the interactions, but it was at par with this. So this is the way how we can execute or perform the analysis of variance in a factorial experiment. But the important point here is that this factorial experiment which we have just learned about, that involves that various factors are studied with equal precision. Now the question is, what will happen when the factors which has got different or same levels but are studied with unequal precision? What strategy we have to execute? So next video will be made on a factorial experiment involving unequal replications. Hope you will like this video. Thank you very much.